Welcome to this neural network programming series. In this episode, we will learn how to build the training loop for a convolutional neural network using Python. Without further ado, let's get started. In the last episode, we learned that the training process is an iterative process. And to train neural networks, we build what is called the training loop. In that episode, we saw how the training process works for a single batch. Now, our task is to extend this idea to all batches in our training set. To do this, we will construct a training loop that will loop over all of our batches. Let's jump over to the code. All right, I'm here in the notebook where we've been working, and we're just going to really quickly go over the code setup to get us to where we need to be in order to build the training loop. So we're going to go over this really fast. So if it's too fast for you, make sure to check out the previous videos where we actually covered all of these steps in depth. Let's go ahead and get started at the top with our imports. We're going to import Torch. We're going to import the neural network package from within Torch. We're going to import functional from within the neural network package. And then we're going to import the Optim package from within Torch. This is where we have a choice of optimizers to work with. Next, we're going to import Torch Vision and transforms from within Torch Vision. The two lines below are just setting up a few things. The first line is setting the line width for output that we get from PyTorch. And then the second line is turning on PyTorch's gradient tracking feature. Now, this is already on by default, but we're going to turn it on here just in case you still have it off from previous episodes when we actually turn this off. Next, we're going to take a look at the Torch and Torch Vision versions that I'm running 1.1.0 for PyTorch and then 0.2.2 for Torch Vision. Next, we have this getNumCorrect function that we defined in previous episodes. All this function does is tell us the number of correct predictions given a predictions tensor and a labels tensor. Next, we have our network definition, and this is the same network we've been working with throughout the series. We're going to go ahead and define that. The network has 2 convolutional layers and 3 linear layers. We have conv1, conv2, fc1, fc2, and the output layer. These layers are being defined in the class constructor as class attributes, and then down in the forward function is where we actually use these. You can see that here where we call self.conv1 in the first line of the for method, and then self.conv2 and so on. All right, the next thing to do is to initialize our training set. And we are using Torch Vision to access the fashion MNIST dataset and pull this into our program. So that's the basic setup that we need to begin the training process. So let's just review what we did in the last episode where we trained or we looked at the training process as it stands with a single batch. So all we did was take a single batch and we looked at how does training actually work given a single batch. The first line is just getting an instance of our network. The second line is getting a data loader to use to get batches. Okay, so we say torch.utils.data.dataLoader. That's saying we want to instantiate a data loader object. To the class constructor of the data loader, we're passing our training set, and we're also passing a batch size of 100. This is going to allow us to ask the data loader to give us batches of size 100 as we train the network. Now, on the right-hand side where we can see the comments, this is what we talked about last time, where this is kind of the general flow of the training process. We want to get a batch, then we want to pass the batch to the network, then we want to calculate the loss, then we want to calculate the gradients, and then we want to update the weights. So in this case, we get our batch, and then we unpack the batch into an images and labels tensor. So once we have our images tensor, we're ready to pass it to the network. So we pass this batch of images, and we get back a prediction tensor for these images. Then we want to calculate our loss. To do so, we're accessing the cross entropy loss function that is coming from the nn.functional interface that we imported at the top. So we get the cross entropy loss function from there, and we pass in our predictions tensor and our labels tensor and we get back a lost tensor. The special thing about this lost tensor is that PyTorch has kept track of all of the computations that led to this lost tensor's creation. So PyTorch can track all the way back until the first operation happened inside the network on the images. So all of these computations are connected, and PyTorch has kept track of these connections using a computational graph. What this allows us to do is calculate the gradient of the loss function with respect to our network's weights. So in the next line, that is exactly what we do with loss.backward. We say calculate the gradients by going backwards on the loss tensor. And backward is short for back propagation. Next, we're going to use our optimizer, and we're going to call step. The step method on the optimizer updates the network's weights. Why can the optimizer update the network's weights? Well, it's because the optimizer knows about the network's weights because we pass the weights into the optimizer's constructor. Network.parameters returns all of the weights of the network. And the second parameter that we passed to the optimizer was the learning rate. The gradients tell us which direction we need to move towards the loss function's minimum, and the learning rate tells us how far do we want to step in that direction towards the loss function's minimum. So because of these two things, after we update the network's weights using those two, we're going to reduce our loss the next time we pass in the same batch of images. So let's run this code and we'll see that actually happen. Because down below, we're going to print the current loss that we got, and then after the weights are updated, we're going to pass the images in again, compute the loss, and we will see that it does decrease. All right, so the loss did indeed go down. And this is how training is done with a single batch. Now what we want to do is move to training with a single epoch. So we're going to go from a single batch to a single epoch. When we cover one single epoch, what that means is that we're covering all of the batches in our training set. So let's take a look at how this is different. So here we basically have the same exact code from before for just doing a single batch. What we're going to do is add a little bit of code here to go across all of our batches instead of just one. So the first thing that we're going to want to do is change how we're getting a batch. So we're going to change this call to get a single batch. We're going to change this to a loop that will iterate over all batches in the train loader. All right, so we're going to say for batch in train loader. This is going to give us the ability to loop over all the batches in the data loader. Now what we want to do is capture a little bit of analytics as this training process happens. So we're going to track the loss and we're going to track the number of correct predictions. So we create two variables at the top of the loop that are initialized to 0. We have total loss and total correct predictions. So we want to just add these up as we go through all the batches. And then at the end, we'll print these out to see what our total number of correct predictions are, and then also what is our loss. And that's all there is to it in terms of iterating over all the batches. However, there is one more important step that we have to add in, and that's due to the way PyTorch calculates gradients. And that's going to be this line here. We need to tell the optimizer to zero out the gradients that are being held in the grad attribute of the weights. And this is because PyTorch accumulates gradients, which just means adds. So whatever the gradient is, when PyTorch calculates a new one, it adds it to whatever it currently is. So for that reason, before we calculate the gradients, we need to make sure that we zero out any gradient values that are currently existing. And to do that, we just say, hey, optimizer, we want you to zero out the gradients, and it'll do it for us. We're going to debug this process in just a second, and this will become super clear. For now, let's just run this code and see what we get. Now, this is going to take quite some time because it's iterating over 60,000 images. Well, it's actually iterating over however many batches we have. So to figure out how many batches we have, we take the total number, which is 60,000, and then we divide that number by the batch size. And that's how we can figure out how many batches we're actually iterating over. And we just finished. So we see we've got a total of 46,000, almost 47,000 correct, and we have a loss value of 348. So back to that thing that I was just mentioning about the total number of iterations. So if we were to take 60,000 and divide that by 100, we would get 600. So we're going to do 600 batches or 600 iterations. Now, something kind of important to take note about this 600 number is that that's the number of times the weights are going to be updated. We update the weights by calling optimizer.step once per batch, every time we come around this loop. So what that means is that we're taking 600 steps towards the loss function's minimum. So just keep that in mind. When you start changing the batch size, you're changing the number of times that we're actually going to update the weights and step in the direction of the loss function's minimum. Okay, now I want to show you actually what it looks like to debug this process. But first, let's just run the total correct divided by the length of the training set. And we can see that we're hitting around 77% accuracy just by doing one epoch. Okay, so let's jump over to Visual Studio Code now, and I want to show you a few things as we debug this process. We have two things that we need to be paying attention to. The first is let's just verify our code on the right. So here are our imports. Here's the getNumCorrect function. We have our network definition. We are bringing in our training set. We're getting an instance of our network, and we're getting an instance of our data loader. We're creating an optimizer, and then we have this same setup here with the loop that iterates over all of the batches. So what I want to do is just put a breakpoint right here at the loop, and then I'm going to hit F5 on my keyboard to start the debugger. Okay, that was left from earlier. All right, so here we are. Execution has stopped at our loop. Now, what I want to be paying attention to on the left are some variables that I went ahead and set up beforehand. So we're going to watch for two primary things that I want to watch for. I've got like the images, tensor shape, and the labels, tensor shape, predictions, tensor shape at the top. But kind of the main two pieces that I want to pay attention to are here. So this first one is the network. We're looking at the network. We're going in and we're getting at the top, we're getting conf1, we're getting the weight tensor, and then we're accessing the gradient values from the weight tensor. And we're just looking at the max value in that gradient tensor. And we're doing that for every single layer. Okay. So that's just going to give us an idea for what our gradients are. Right now, they don't have a value because they haven't been defined just yet. Then the next thing I want you to pay attention to is down the next little group of kind of layers here is going to be the network.conf1.weight.max. So we're just looking at essentially the gradient values for the weights, and we're looking at the weights themselves. And we're not actually looking at all of the weights or all of the gradients. We're just looking at the max value. So we just want to kind of get a sense for what's there by looking at the max value. So let's go ahead, and I'm just going to start stepping over this code, and we're going to take a look at what happens. So now we have a batch and we're inside our for loop. Now, once we unpack the images and label tensors, that's when we'll see the shapes show up on the left. So we have the images shape and we have the label shape. The images shape is 100 by 1 by 28 by 28. So I hope you can see that the 100 is the batch axis. And so since we defined our data loader to have a batch of 100, it's going to give us batches of 100 back. And that's why we have a 100 in the batch axis. Then the next axis is the channels axis. And we have a single color channel for these grayscale images. And then our images are 28 by 28 with height and width. So that's the interpretation of this shape for the images tensor. And then for the labels tensor, we need to have corresponding labels for every image, and that's why we have 100. So let's go ahead and pass this batch of images to the network. Okay, and now we have a predictions tensor, and if we look at its shape, the shape of it is 100 by 10. So what this is 100 images, and for each of them, there are 10 categories, and the network has given us a prediction for each category. The category that has the highest prediction is the category that the network is predicting most strongly. Okay, so now we will calculate our loss by passing the predictions tensor and the labels tensor to the cross entropy loss function. And we get a loss value. Now we're going to zero out our gradients. So this is the call that I really wanted you to pay attention to. This time, actually, nothing's going to happen because the gradients haven't been defined yet. But when we come back around in this loop, this one we'll really see this one, see exactly what it does. So let's just step over that, and we're ready to calculate our gradients. As soon as we call backward on the loss tensor, we're going to see all the gradients of the network get populated. Now we actually have values inside the grad attribute of our weight tensors. So we'll call optimizer.step, and we'll see our weights actually update. Okay, so the weight's updated. We can track our loss, track our total number correct, and we're ready to get the next batch. So let's just go ahead and grab the batch, unpack it, pass it to the network. Now we have the predictions. We take the labels predictions, calculate the loss, and now we're back here at the moment when we need to zero out our gradients. So watch what happens when we run this line. We're going to see that our gradient values, which are now positive, are going to go to 0. So here we go. So now all of our gradients are back to 0. When we call backward on the loss function, the new gradients will be calculated and they'll be added to these current values. So if those current values weren't 0, then we'd basically be accumulating gradients. And for standard networks like this one, we don't want to do that. That's why we need to zero them out. So we'll go ahead and step over. We get new gradients. Now we call step and we get new weights. All right, track the loss, track the total correct, and we just keep doing this over and over again until we've gone through all batches and we've completed a single epoch. So in summary, we get a batch, we unpack it, we pass it to the network, we get predictions. We pass the predictions and the labels to the loss function and we get the loss. Then we zero out our gradients and we calculate new ones, and then we update the weights. The weight update step uses the gradients and the learning rate, which is defined at the top in the optimizer's constructor, 0.01. We use the gradients to tell us which way we need to step, which direction is the loss function's minimum, and we use the learning rate to tell us how far in that direction we need to step. And when we do, our weights update, and those weight updates happen in such a way that the next time this batch gets passed in, the loss will be lower because we moved the computation of network in such a way that it will give us a lower loss. And that's how we do a single epoch. So we've gone from a single batch and now we've done a single epoch. So to complete the actual training loop, we need to do multiple epochs. So essentially we do this process that we just looked at over and over again for many epochs. So let's jump back over to the notebook and see how this is done. All right, so we're here in the notebook and this is the complete training loop. All we have to do to make this process a training loop and create multiple epochs is take that code that we were just inspecting and put it inside of a loop like this for epoch in range. And then however many epochs we want to do, we put that number right here, and that means we're going to do 5 epochs. So let me just show you. If we grab this code that we were just looking at, and then we paste that code here, everything is the same except for this. So we need to change this. Before, we only had just one epoch that we were doing. So we said this is the 0th run. But now we actually have a variable for that. So we can put that variable here. So we're going to run this code. We're going to see the training loop in action. All right, so the training has completed and we can see that every epoch run, our accuracy was going up, but it did start to kind of slow down at the 5th epoch. What happens typically in the training process is you will see these kind of quick improvements, and then at some point though, you'll start to run up against a little bit of a plateau. And at that point, that's when you'll start having to think about tuning or changing your hyperparameters, changing your network's architecture.
And you may be wondering, what if my model just flat out sucks? Well, in this case your model may be underfitting to the data. To find strategies to fix this, check out the underfitting video in the Deep Learning Fundamentals series.
So let's just run this code here, and we can see that we are at about 88% accuracy at the current moment after 5 epochs. And this is the complete training loop with a CNN built in PyTorch. If you haven't already, be sure to check out DEEPLIZARD.com, where there's a blog post for each episode. And there's even quizzes now, so be sure to check that out. Don't forget about the DeepLizard HiveMind, where you can get exclusive perks and rewards. Thanks for contributing to Collective Intelligence. I'll see you in the next one.
Hello. Think about this. This is important for the AI community, the engineers like yourself who are learning about and building AI systems. There are these hypothetical future scenarios that envision AI runaway systems. Under this assumption, these AI systems with a goal might go rogue. By this, I'm talking about unintended consequences. Like the automobile. These things are rubbish polluters and have shaped the formation of all of humanity's cities. Some people think this is the future. However, what if I told you that this is already the case? What if this is indeed the case for things like the Facebook newsfeed and the YouTube recommendation system? These artificial intelligence systems are controlled by companies. These companies are incentivized to make a large profit. If the AI systems are doing their jobs, then, I ask you, is it possible for these companies to turn them off? Is it even legal for them to do so? Even if the AI systems are working by hijacking the attention spans of humans at large. Let's say 2 billion humans more or less controlled by these systems, spending every waking moment staring at their devices. Well, I'd say, engineers of the future have much to consider.